Hello and welcome back. In 11.6, we work on conditional probability. So the idea of conditional probability is we're sort of restricting our search area. The notation, probability of event A given event B, is the probability that both events happen out of the probability that the given condition has occurred. So notice division is not a commutative operation, so the order that we write this does matter. So B is the given condition. So we'll start with a little table. We'll look at then some card examples, some dice examples, and go over a very famous problem. So we'll start with what's called a two-way table. So we're sorting data by two different types of variables. So in this one, we have major and year. Let's see, 20, 60, 80, and 40. So then we get what are referred to as the marginal totals. So this study had 80 freshmen, 120 sophomores, for 200 students altogether. Looking at the other variable, we had 100 math majors and 100 English majors. So first we'll look at the probability that a randomly selected student is a freshman. So again, we're assuming random selection. And if you take a stats course, you can go into a little more detail on how to make sure that your sample is randomly selected. But for now, we'll just assume that we correctly randomize this experiment, and we want the probability of selecting a freshman. So at the moment, I don't care about major. If they're asking for freshmen only, we have 80 freshmen out of 200 students. So 8/20, both divisible by 4, so 2/5. Next, we'll look at the probability of randomly selecting a freshman, given that we are looking at a math major. So let me just write that descriptor below. We're not going to write that every time, but I just want to make sure we're all on the same page. So this is the idea. Now we're selecting a freshman, given that we're only focused in on, in this case, math majors. So my area of concentration, now I only see this top row. So the intersection of F and M, freshman math majors, we have 20 of those out of the math majors. We have 100 math majors. 2/10 is 1/5 different probability, depending on what we're looking at. So let me have you all try a couple out. We'll use the same table. I'll ask you to find probability of M, probability of M given F, and probability of M given E. So go ahead and pause it, see if you can find those three probabilities based on what we've seen so far. Welcome back. So the probability of randomly selecting a math major. So last time when we were talking freshman, sophomore, I only cared about these marginal totals. Now that we're talking math major or English major, I'm only caring about the blue totals. So we have 100 math majors out of 200 students altogether. Probability of selecting a math major in this circumstance would be 1/2. Don't forget your labels. Then we'll look at the probability of selecting a math major given that we are selecting from freshmen only. So we're looking at freshman math majors, 20 of those out of total number of freshmen. So the given condition says, given that we're working with freshmen only, I'm only concentrating on this much of the chart. So 20 out of 80, 2/8 is 1/4. Again, different values. Probability of a math major, given that we're working only with sophomores. My apologies, I don't know where I got that from. So go ahead and pause it if you need to. Try the math given sophomore. Welcome back. So math majors that are sophomores, we have 80 out of the number of sophomores. Sophomores, we had 120. So 8/12, both divisible by 4. So 2/3. One thing I wanted to point out, F given M and M given F, two different values. Remember, this is not a commutative operation. The order does matter to us. All right, so next we will roll a die. Actually, I think I'll have you all try the die rolling. We'll do the cards together. So our next experiment, we will draw a card. And we'll look at the probability of randomly selecting a 2. Well, there are 4 cards in the deck marked with a 2 out of 52 cards in the deck. These are both divisible by 4, 1/13. And that should fit with what we know about the suits. There are 13 cards in each suit, one of which is marked with a 2. Next we'll look at, though, the probability of a 2 given that we have something that is not a face card. So the number of cards that are both 2s and not face cards would be 4 of those out of the given condition, not a face card. So we have 12 face cards in the deck, Jack, Queen, King in every suit. So 52 minus 12, we have 40 other cards. So 1 in 10. So our odds increase. We have a better chance of selecting a 2 under this given condition. So we have you all try again another experiment. This time we will roll a die. And I want you to find the probability of randomly rolling a 5 and the probability of rolling a 5 given that your roll was odd. Let's go ahead and pause it if you need to. Unpause it when you're done. Okay, rolling a die. There's only one side that has a 5 on it out of 6 sides total. 5 given that we're working with odds only. Again, there's only one card that's both a 5 and odd, or one side that's both a 5 and odd, out of only 3 sides that are odd. So I've doubled my chances if I'm stating the condition that we already know the roll was an odd number, which is what this conditional probability is. So the next thing I want to talk about is one of our most famous recent math problems. It's referred to as the Monty Hall problem. So the idea here is there are 3 doors. One has a prize. For this experiment, we'll refer to it as a car. And 2 are things that are not desirable. For the purposes of the famous Monty Hall problem, the goat. So you have a contestant, and they say a door number. That door is not opened yet. The host, Monty Hall, will open one goat door. Then it's up to the contestant keep original guess or switch. So this is a problem that at first sounds like it should be a 50-50 enterprise. There's 2 doors remaining. One has the car in it, one has a goat in it. There were 2 goats at the start. They showed us where one of them was. We're definitely not picking the goat that they revealed to us. It sounds like it should be an even shot, but it's actually due to conditional probability that it really is not. So let's look at how that happens, why that happens. So for the sake of our experiment, we'll assume that door number 1 has a goat, door number 2 has the car, and door number 3 has the other goat. So Monty Hall knows this, and that's part of the conditional probability. The host knows the solutions. So our contestant let's say they pick right. and first guess. So the contestant guessed door number 2. Monty Hall opens, let's say, door number 1. If the contestant keeps their guess and they picked right on the first guess, they win. Congratulations, you win a car. Otherwise, they get a goat. We don't want to get a goat. So on this one, if the contestant is ignoring what Monty Hall shows them and just keeping their original guess, the probability of a win is just based on the likelihood of their guessing it the first try. Backwards, probability of a win, 1 correct door out of 3 doors if we're ignoring Monty Hall. Case 2. Contestant picks wrong on first guess. So let's say for the just without loss of generality, they pick door number 1. Monty Hall will open door number 3. They keep their guess. They lose. They change. They win. So they've guessed door number 1. In that case, Monty must open 3 and show the goat. They keep their door, they will lose. They change their door, they'll win. In other words, in this one, what's easy to miss is this key here. If they change their guess, they'll win when their guess is wrong in the first try. What's the probability that their guess was wrong in the first try? 2 out of 3. You actually double your chance if you change your door in the Monty Hall problem. So even though it sounded like a 50-50 shot, there's one with the car, one with the goat, it sounded like a coin toss because of the condition that Monty Hall knows where those goats are. It's actually to your advantage to switch your guess. That was a controversial problem at the time. Marilyn Vos Savant, one with one of, if not the highest recorded IQ, she wrote a column and answered different questions people would pose, and she had this right. And there were many people, including people with PhDs in math, that told her she was wrong. She was absolutely right on this. And you can even find online simulators. I'll challenge you to look for that. Find an online simulator. And you can have it run 100 trials, 1,000 trials, and you can actually find that the data does support the sort of counterintuitive conclusion that changing your guess does give you better odds than keeping it. And the basic idea of that, again, is all you have to do if you're changing your guess is guess the wrong one on the first try. The other wrong one will be eliminated for you, and flipping it guarantees a win. And there's a 2 out of 3 chance that you will have guessed the wrong door in the first place. So again, just a fun, famous math problem involving conditional probability. Some problems that I would try out of 11.6, I would try 5 to 83, every other odd again. So if you have any questions, please get in touch. Otherwise, I'll see you for the next section, and stay safe out there.